The Milky Way has 4 major spiral arms, and our solar system is not in any of them. It sits in a smaller feature, a kind of secondary structure tucked between 2 of the major arms, a place that most textbooks label a spur or a minor arm, and then move past quickly. The name of this structure is the Orion Arm, and the problem with understanding it is not that the information is scarce. The problem is that we are inside it. Think about what that means for a moment. Every measurement, every estimate, every map of this structure has been made from one fixed point, here. A single solar system on the inner edge of the very feature being described. There is no angle from which to step back. There is no outside view. Astronomers trying to determine how wide the Orion Arm is, how long it runs, where exactly we sit within it, are doing something like trying to measure a room while standing in the middle of it with no walls in sight. The room is too big to see across. The tools available are precise, but the position is never ideal. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Here are the questions that drive the problem. How wide is the Orion Arm? How long does it actually run? Where are we inside it? Near the center? Near an edge? Near one end or the other? And why, given that we are embedded within this structure, does the solar system feel so profoundly alone? The nearest star beyond our own is 4 light-years away. The nearest significant cluster of star formation is hundreds of light-years distant. In every direction, there is mostly emptiness. That emptiness is strange, and it turns out to have an explanation. The standard description of the Orion Arm treats it as a minor player in galactic terms, a spur, a connecting bridge, something that fills in the space between the Carina-Sagittarius Arm and the Perseus Arm, without quite rising to the level of a real spiral arm. Textbooks have called it this for decades, but when you actually sit with the numbers, something starts to feel wrong about that framing. The arm is roughly 3,500 light-years wide. Its length, based on measurements made in just the last few years, extends to at least 26,000 light-years. That is a span equal to the entire distance between the solar system and the center of the galaxy. Minor is a word that stops working at those scales. Something labeled minor should not be capable of swallowing those distances. Scientists have had to revise their picture of this structure multiple times in the last 2 decades alone. Older estimates put the arm's length at somewhere between 10,000 and 20,000 light-years. New data, built on techniques that did not exist a generation ago, pushed that figure upward dramatically. The arm grew in the data, and alongside those revisions came others. Revisions to the distribution of star-forming regions within the arm. Revisions to the large-scale structures that organize those regions. Revisions to the frameworks that astronomers had trusted for over a century. The picture is sharper now than it was in 2000. It is sharper now than it was in 2015. And there is no particular reason to believe it has stopped changing. What makes our position in this arm genuinely strange is not just the scale, it is the specific nature of the space around us. The solar system is not sitting in a typical patch of the Orion Arm's interstellar medium. It is sitting inside a cavity, a roughly spherical region of extremely low-density gas, much thinner than the surrounding arm, extending roughly 1,000 light-years across. The material that should be there, the gas and dust that fill most of the arm's interior, has been cleared away. What remains is hot, thin, and almost empty by galactic standards. This cavity has a name, the local bubble, and it is the reason the solar system's immediate neighborhood feels so sparse compared to the arm it inhabits. That cavity was not always here. It was not part of the original structure. It was made. And the stranger part is that the emptiness surrounding us was put there on purpose by forces that finished their work about 14 million years ago, long before anything on Earth could look up and notice. To understand what the Orion Arm is, you first need to understand what it is not. It is not one of the Milky Way's main spiral arms. When astronomers draw the galaxy from above, the features that dominate the picture are four primary structures: the Perseus Arm, the Scutum-Centaurus Arm, the Norma Arm, the Carina-Sagittarius Arm. These are the major players. They are massive, dense, and packed with both ancient stellar populations and newly forming stars. The Orion Arm is not among them. It sits between two of these major arms, tucked in the space between the Carina-Sagittarius Arm on the side closer to the galactic center, and the Perseus Arm on the side facing outward toward intergalactic space. In galactic terms, it occupies the gap. That distinction matters more than it might initially seem. The official name is the Orion-Cygnus Arm. You will also see it called the Local Arm, which is a name that sounds almost deliberately modest. Both names are in common use, and the choice between them tends to reflect something about how seriously the writer takes the structure. Orion-Cygnus emphasizes its extent across a significant stretch of sky. Local Arm is the name you use when you are treating it as a regional footnote to a larger galactic story. The difference in naming is not purely cosmetic. It reflects a genuine, long-running disagreement about what kind of object this actually is. What separates a major spiral arm from a minor one comes down to composition and density. Major arms carry enormous populations of old red and yellow stars alongside their younger blue and white counterparts. Those ancient stellar populations make the major arms structurally thick, gravitationally substantial, and relatively permanent features of the galaxy's architecture. The Orion Arm does not have that deep reservoir of old stars. What it has instead is gas. Enormous quantities of it. Cold molecular clouds, dense hydrogen filaments, stellar nurseries still in the process of building new stars. The arm is primarily a star-forming structure rather than a stellar storage structure. It is less a library and more a factory floor. Loud, active, full of raw material being assembled into something new. This is why the constellation Orion gave the arm its name. Nearly everything that makes Orion recognizable to people standing outside on a winter night is a resident of this arm. Betelgeuse, the red supergiant marking the hunter's right shoulder, is roughly 700 light-years away and embedded in the same structure we inhabit. Rigel, the brilliant blue-white star at the opposite corner, sits about 860 light-years out and belongs to the same arm. The three belt stars, Mintaka, Alnilam, and Alnitak, are all Orion Arm residents. So is the Orion Nebula, that faintly glowing smudge below the belt that the naked eye catches as a slightly soft star, which is in reality a region of massive star formation, roughly 1,340 light-years away. That nebula is not a background object. It is practically a neighbor, at least by the standards of galactic distance. When you look at Orion on a clear night, you are looking into the arm. You are seeing a cross-section of the structure we live inside. For most of the 20th century, the classification of this arm was not treated as a serious open question. Astronomers had a label for it and moved on. The label was spur. A spur is exactly what it sounds like. A short, secondary feature branching off one of the major arms, not a genuine spiral arm in its own right. The thinking was that the Orion Arm was essentially a bridge of material connecting parts of the Perseus and Sagittarius arms, without the mass or extent to qualify as a real structural member of the galaxy. Textbooks used this framing. Radio surveys supported it, more or less. The arm was real, but it was minor in a way that discouraged further argument. The trouble was that spur classification required the arm to be relatively short. Estimates based on radio mapping of hydrogen gas put its length somewhere around 10,000 to 20,000 light-years, which was consistent with the idea of a modest connecting feature rather than a full spiral arm. Those numbers came with uncertainty, but they felt reasonable enough that the classification stuck. No one had a strong reason to challenge it. Then the measurements got better. By the time high-precision parallax data began arriving from targeted surveys of maser sources in star-forming regions, the arm started looking considerably larger than the spur model predicted. Evidence accumulating around 2013 pushed the picture further. Some researchers concluded that the Orion Arm was not a spur at all, but a branch of the Perseus Arm. a structure that had split off from one of the major arms and developed its own coherent existence. Others argued it was something different still, possibly an independent arm segment that did not connect cleanly to either neighbor. Neither position was easily dismissed, and neither was easily confirmed. What made the debate stubborn was the nature of the evidence. Mapping a spiral arm from inside it is not a clean process. Every measurement comes with assumptions about stellar distances and gas velocities that can be challenged. When the data sits in a range that permits multiple interpretations, classification arguments have a way of persisting. Different researchers using different methods reached different conclusions. Conferences produced papers that contradicted other papers from the same year. The arm resisted easy categorization, not because it was featureless, but because its features could be read more than one way. The classification debate had not been settled in 1980. It had not been settled in 2000. And in certain meaningful ways, it had not been settled by the time the most important observational campaigns of the 21st century got underway. The number that keeps stopping people is 3,500 light-years. That is the width of the Orion Arm, measured roughly from its inner edge to its outer edge, the short dimension, the narrow side. And it already doesn't fit inside anything a human mind was built to hold. Start with something closer. The nearest star beyond our Sun is Alpha Centauri, sitting about 4 light-years away. At the speed of light, you cross that gap in 4 years. The Orion Arm is 875 times wider than that distance. If you lined up 875 copies of the journey to Alpha Centauri end to end, you would just barely span the arm from one side to the other. And that is the width. The short direction. Now take the length. Older estimates, based on radio observations made through most of the 20th century, put the Orion Arm at somewhere between 10,000 and 20,000 light-years long. Those numbers were already beyond imagining. Then the BeSSeL Survey published its results, and the arm grew. New measurements, built on direct geometric parallax of maser sources in star-forming regions, pushed the length to at least 26,000 light-years, 4 times larger than what the textbooks had been printing for decades. Not a refinement, a fundamental revision. Consider what 26,000 light-years actually means in terms of time. Light leaving the far end of the Orion Arm right now will not reach us for 26,000 years. That number needs a frame of reference to land properly. 26,000 years ago, anatomically modern humans were living in small groups across Europe and Asia. They were painting animals on cave walls in France and Spain. Bison, horses, hands pressed against stone and blown with pigment. Agriculture did not exist. Writing did not exist. The wheel did not exist. Every civilization in human history, every city ever built, every war ever fought, every name ever recorded, has happened inside the time it takes light to cross from one end of this arm to where we sit in the middle of it. And the arm is so long that light from where we are right now will not reach its far end for another 13,000 years. If the Milky Way was scaled down to the size of North America, the whole continent stretching roughly 4,500 miles from coast to coast, the Orion Arm would run for something close to the length of California, the entire state, end to end, and it would be about the width of a city block, a long thin stripe of a state running diagonally through one corner of the continent, and our solar system would be somewhere near the middle of that stripe, a speck too small to see with the naked eye on any map printed at that scale. The width again, 3,500 light-years. To cross it at the speed of light would take 3,500 years. The entire span of recorded human history, from the earliest writing systems in Mesopotamia to the present day, covers roughly 5,000 years. Cross the arm's width at the speed of light, and you would arrive having consumed nearly all of that time in transit. Do it again, and you have spent longer traveling than humans have been keeping written records. The arm is 875 times wider than the nearest star. It is 3,500 years across at light speed. It stretches for 26,000 light-years end to end. These numbers do not add up to something graspable, no matter how many times they are approached from different angles. They are simply too large. The human brain was shaped by selection pressures that never once required it to model distances beyond a few hundred miles. Everything past that is abstraction. The Orion Arm is an abstraction built on top of an abstraction, the kind of scale where the analogies eventually run out and you are left standing with a number that points at something real without ever quite touching it. What makes this stranger still is the shape of the arm relative to where we sit inside it. We are roughly at the arm's midpoint along its length, meaning there is something close to 13,000 light-years of arm extending in each direction from our position. The arm is not something we are near the edge of. We are submerged in it, surrounded by it on every side, and the boundaries in each direction are so remote that the light carrying information about them has been traveling since before recorded civilization began. Betelgeuse, one of the arm's most famous residents, sits about 700 light-years away. That is close enough for its light to reach us, in roughly the same time it took for Europe to go from the beginning of the Renaissance to now. And Betelgeuse is practically a neighbor inside the arm's full extent. The Orion Nebula, the nearest major region of active star formation to Earth, is roughly 1,340 light-years away. Still well within the arm's width, still less than half the distance to the arm's inner edge. The arm is 26,000 light-years long. It is 3,500 light-years wide. It contains molecular clouds, stellar nurseries, supergiants, nebulae, and hundreds of billions of stars distributed through its volume. Its length now rivals the distance from Earth to the galactic center, and this is the minor arm. The solar system's position within the Orion Arm has a specific address. It is not a glamorous one. Sit with the coordinates for a moment. We are close to the arm's inner rim, roughly halfway along its total length, approximately 26,000 light-years from the galactic center. That places us about 2/3 of the way out from the core of the Milky Way, not in the dense, chaotic interior, not at the quiet outskirts, but somewhere in between, in the galactic equivalent of the suburbs, the kind of neighborhood that does not appear on any tourist map. Being on the inner rim means the Sagittarius Arm sits closer to us than the Perseus Arm does. The Perseus Arm, one of the Milky Way's two true major arms, lies roughly 6.000 to 7,000 light-years away in the direction of the Perseus constellation. The Sagittarius Arm is in the opposite direction, at comparable distance, curving inward toward the galactic center. We are wedged between them, in the thinner structure in the middle, close enough to the inner edge that we lean slightly toward the galactic interior. Being halfway along the arm's length is its own kind of isolation. The full extent of the Orion Arm stretches at least 26,000 light-years from one end to the other. We sit somewhere near the midpoint. Neither end of this structure is anywhere near us. The molecular clouds, the stellar nurseries, the vast formations of gas at the arm's far reaches, all of it exists at distances that light would need tens of thousands of years to cross. We are not at the edge of something, where at least one direction opens into emptier space. We are surrounded by arm on all sides, embedded in it, with no easy boundary nearby in any direction along the arm's length. Now look toward the galactic center. In the direction of the constellation Sagittarius, there is something enormous sitting 26.000 light-years away, a supermassive black hole called Sagittarius ASA, surrounded by a dense bulge of ancient stars, intense radiation. Radio noise that telescopes can detect from here with no trouble. In radio waves and infrared, the galactic center is not subtle. It blazes, but in ordinary visible light, you cannot see it at all. The reason is dust. The disk of the Milky Way is full of interstellar dust, not the kind of dust you find on a shelf, but vast clouds of tiny particles of carbon and silicate that absorb and scatter visible light with extraordinary efficiency. Between us and the galactic center, across 26,000 light-years of the disk, there is enough dust to block all visible light from that direction entirely. The center of our own galaxy is invisible to the naked eye. It is invisible to optical telescopes. It sits behind a wall of interstellar material so thick that it might as well not exist. As far as visible light is concerned, astronomers only cracked this open in the 20th century when radio telescopes came along. Radio waves passed through dust almost without interruption. Suddenly, the galactic center was reachable. Then came infrared observations, longer wavelengths of light that slipped past dust particles that would stop visible photons cold. With infrared and radio, the center became visible for the first time. What was there was stranger and more violent than anyone had expected. An entire hidden cosmos, sitting 26,000 light-years away, completely masked by the same disk of material that our solar system is embedded in. This creates a peculiar situation. We live inside the galaxy, and yet we have never seen its actual structure. Not directly, not the way you can see a spiral galaxy in a photograph, stepping back and watching the arms curl away from the center. We have always been inside the thing we are trying to describe. The material surrounding us blocks most of the view. Mapping the Milky Way from this position is something like trying to draw a city while standing at an intersection. Buildings on every side, with no way to get altitude. You look in one direction and see a street. You look in another and see a different street. You make measurements, count the buildings, estimate the distances, slowly build a picture of something you can never directly observe. Every map of the Milky Way is an inference. It is the conclusion of very careful reasoning from very constrained evidence, not a photograph of a thing observed from outside. What this means for our specific address is that even the coordinates themselves were not easy to establish. The distance from Earth to the galactic center was not known with any precision until the mid-2030 century. It has been revised multiple times since. Our position along the arm's length was murky for decades because measuring distances to objects across thousands of light-years requires techniques that only recently reached sufficient precision. The very fact that we sit near the inner rim rather than the outer rim, that we are roughly at the arm's midpoint rather than nearer one end, these are conclusions that required generations of astronomical work to arrive at, using radio telescopes, infrared observatories, eventually spacecraft precision measurements that were not available until the last few decades. The address has a kind of quiet finality to it. Inner rim, midpoint of the arm's length, 2/3 out from the galactic center, inside a region of relatively low density, in a bubble of cleared out interstellar gas. Looking toward a galactic center we can only observe in wavelengths of light the human eye cannot see. Nothing about this location stands out. Nothing marks it as special. We are on the inner edge of a minor arm, in a low-density region, in the suburbs of a galaxy that itself is not particularly remarkable, and every attempt to figure out where we are exactly has required dismantling assumptions that seemed obvious at the time. Here is the detail about our location that most people never hear. The solar system is not simply sitting inside the Orion Arm the way a marble sits inside a bowl. It is sitting inside a cavity within the arm, a hollow region, a carved-out pocket of space where the gas density is roughly 1/10 of what it is in the surrounding interstellar medium. Astronomers call this structure the local bubble, and it is approximately 1,000 light-years across. The material filling it is not the kind of cold, dense gas you find in molecular clouds. It is plasma, extremely thin, heated to somewhere around 1 million Kelvin. That temperature sounds extreme, but the gas is so sparse that the actual energy content is almost nothing. It is a hot vacuum, more than anything resembling a surface or a substance. For context, the average interstellar medium in the Orion Arm contains roughly half a hydrogen atom per cubic centimeter. Inside the local bubble, that number drops to about 1/20th of an atom per cubic centimeter. The difference is not subtle. Step outside the bubble and the medium gets dramatically denser. Inside it, the solar system moves through something that is effectively one of the emptiest environments in the arm. This is our immediate neighborhood. This is what surrounds us in every direction for hundreds of light years. The bubble did not form slowly. Something blasted it open about 14 million years ago. A population of massive stars in a nearby association called Scorpio Centaurus began dying. Massive stars die violently. They collapse and detonate in supernovae that release more energy in a few seconds than our sun will emit across its entire lifetime. One supernova is enough to reshape the interstellar medium for hundreds of light years in every direction. What happened near our current location was not one supernova. Current estimates suggest at least 15 of them, possibly more, going off over a span of millions of years in roughly the same region of space. Each explosion drove a wave of energy outward, pushing the surrounding gas away, compressing it, heating the remaining material into the thin hot plasma that fills the bubble today. The cumulative effect of all those detonations was this hollow region, roughly spherical, roughly 1,000 light-years wide, sitting inside the Orion Arm, like an air pocket inside a loaf of bread. None of this happened while the solar system was here to witness it. The solar system is 4.6 billion years old. The local bubble is 14 million years old. And the solar system did not move into its current position within the bubble until quite recently. On astronomical timescales, the solar system has been inside this cavity for a relatively short time. The bubble was already ancient, in human terms, by the time the sun arrived. This is not the solar system's original address. It is a more recent one. Now here is where the consequence of all this becomes strange. The explosions that hollowed out the local bubble did not simply push gas away into nothing. They drove that gas outward and compressed it at the bubble's walls. Compressed gas, under the right conditions, collapses. Collapsing gas ignites into stars. The supernovae that carved the emptiness surrounding us also triggered new star formation at the edges of what they carved. Look at where the active star-forming regions sit in our cosmic neighborhood, and the pattern becomes clear. Taurus, Perseus, Ophiuchus, the molecular clouds where new stars are being born right now, within a few hundred light years of Earth, are clustered at or near the boundary of the local bubble. They are sitting on the shell. The same ancient violence that created our emptiness created their density. We are living in the quiet interior, surrounded by a ring of stellar nurseries that owe their existence to the same catastrophic events that gave us our hollow. This is a kind of irony that takes a moment to land. The reason our immediate neighborhood is so low density, so sparse, is the reason our neighborhood's edges are so active. The forces that cleared the space we occupy are the forces that built the star-forming regions we can observe from inside that space. We see Taurus as a dark cloud threaded with young stars, a few hundred light years away. We are seeing a piece of the bubble's wall, the compressed remnant of a shockwave that finished its outward push millions of years ago and left its material stacked up at the boundary. Even within the local bubble, the solar system is not simply drifting through uniform emptiness. There are smaller, denser clouds threading through the bubble's interior. The solar system is currently passing through one of them. It is called the local interstellar cloud, a wisp of partially ionized gas, cooler and slightly denser than the surrounding bubble interior, which the solar system began moving through only about 10,000 years ago. That crossing is ongoing. We are inside this smaller cloud right now, moving through it. How long the transit will last is not precisely known. Estimates range from a few thousand to tens of thousands of years, from now before the solar system emerges into the emptier regions of the bubble again. Before that, and for most of its history, the solar system was somewhere else inside the Orion Arm. Somewhere denser, somewhere more crowded, somewhere that looked nothing like the relatively quiet pocket of space we currently occupy. One of the stranger facts in all of astronomy is that we know the structure of galaxies millions of light years away better than we know the structure of the one we live in. It sounds wrong. It sounds like the kind of thing that gets said for dramatic effect and then quietly walked back. But it is not wrong. We have detailed maps of spiral galaxies 30 million light years away. We can trace their arms, measure their bars, count their satellite companions. The Milky Way, the galaxy we have been embedded in for 4.6 billion years, remains genuinely difficult to read. The reason is simple and frustrating in equal measure. You cannot see the shape of something when you are standing inside it. Think about what that actually means for an astronomer. Every telescope on Earth is pointed outward from a single fixed position inside the galactic disk. There is no angle from which we can look down and see the full structure spread out below us. There is no elevated vantage point. Everything we know about the shape of the Milky Way has been assembled from observations made inside it, the way you might try to draw a city map by standing at one intersection and looking in every direction, rotating slowly, guessing at distances. You can see what surrounds you immediately. What is far away blurs and obscures behind the near. And then there is the dust. The Milky Way's disk is not empty space. It is threaded with clouds of interstellar dust, fine particles that absorb and scatter visible light with remarkable efficiency. In most directions along the galactic plane, visible light can travel only a few thousand light-years before it is completely absorbed. The galaxy is roughly 100,000 light-years across. A few thousand light-years of visibility is like trying to see across a continent through thick fog, managing to make out the next neighborhood, and then nothing beyond. For most of the 20th century, the spiral arms of the Milky Way were simply invisible to optical telescopes. The structure was there, the light carrying information about it never arrived. This is the problem that radio astronomy was built to solve. Radio waves pass through interstellar dust almost without interruption. In the late 1940s and early 1950s, astronomers realized that neutral hydrogen gas emits radio waves at a very specific frequency, 21 centimeters. Hydrogen is the most abundant element in the galaxy. It fills the spiral arms in enormous quantities. If you could detect the 21 centimeter signal from hydrogen clouds across the galaxy, you could map where the gas was concentrated, which meant mapping where the arms were, regardless of what dust was blocking the view. The first radio maps of the Milky Way's spiral structure appeared in the 1950s. They were crude but transformative. For the first time, astronomers could see spiral features extending across the galaxy at distances no optical telescope could reach. Arms were identified. Structure began to emerge. It was a genuine breakthrough. But radio mapping carried its own blind spot. Detecting a hydrogen cloud tells you its velocity. It does not directly tell you its distance. To convert a measured velocity into a distance, you need a model of how the galaxy rotates, how fast gas at different radii is moving. That model requires assumptions, and the assumptions are not always correct. Gas clouds in spiral galaxies do not move in perfect circular orbits. They are tugged by the gravity of the arms themselves, by nearby massive objects, by the chaotic local dynamics of star-forming regions. The velocity-to-distance conversion can be wrong by thousands of light-years in some cases, and there is no straightforward way to know when it has gone wrong. Early radio maps placed spiral arms with considerable confidence. Later, when better data arrived, those arms shifted. Features moved. Some structures that looked like a single arm turned out to be two. Some arms that appeared continuous had gaps. The maps were revised, then revised again. Each revision was presented as progress, which it was, but each one also underlined that the previous version had been wrong in ways that had not been obvious at the time. What astronomers needed was a way to measure distances directly, not inferred from velocity, not derived from assumptions about galactic rotation. Actual geometric distances, the kind a surveyor would recognize. This is where the maser sources came in. Masers are natural amplifiers of microwave radiation. They occur in specific conditions, often in dense clouds around newly forming massive stars. They are extraordinarily bright at radio wavelengths, detectable across enormous distances. And because they are associated with high-mass star-forming regions scattered across the galaxy, they are embedded precisely in the structures astronomers most want to map. The key measurement is parallax. As Earth orbits the Sun, nearby objects appear to shift very slightly against the background of more distant objects. Measure that shift, apply basic triangular geometry, and you have a direct distance. No assumptions about rotation. No velocity models, pure geometry, the same technique that has been used by surveyors on Earth for centuries, extended across thousands of light years with radio telescopes sensitive enough to detect the shift. The resolution required for this is extraordinary. Measuring the parallax of a maser source several thousand light years away requires angular precision finer than a human hair seen from the distance of the Moon. The Very Long Baseline Array, a network of radio telescopes spread across the continental United States, can achieve exactly this. The BeSSeL Survey was built around it. The results, when they came in, changed the map of the Orion Arm more dramatically than any previous revision. The galaxy we live inside has been harder to map than galaxies we can never visit, and every time we developed a better tool for looking, the map changed. For 150 years, the model for star formation in our corner of the Milky Way was built around a structure called the Gould Belt. Benjamin Gould identified it in the 1870s, a ring of bright stars and molecular clouds, tilted roughly 20 degrees relative to the galactic plane, spanning about 3,000 light-years in diameter, centered more or less on our solar system. That last detail should have raised more questions than it did. Instead, the structure was accepted, named and handed down through generations of astronomy textbooks as the standard framework for understanding local star formation. For over a century, it organized everything. When astronomers studied Taurus, they placed it in the Gould Belt. When they studied Perseus, Ophiuchus, Orion, same answer. These clouds scattered across hundreds of light years were understood as pieces of a single coherent ring structure, tilted at that characteristic angle, rotating slowly as a unified feature. Graduate students learned its geometry as settled science. Observing proposals referenced it. Research papers assumed it. If you wanted to understand why star formation in our neighborhood looked the way it did, the Gould Belt was the explanation you reached for first. The problem was always there, quietly waiting. It was not a problem with the data. The observations that revealed the belt were real. The stars were where Gould said they were. The associations of young massive stars were genuinely there. The clouds were bright and visible. The problem was with the interpretation. The Gould Belt required a physical mechanism to explain it, and that mechanism was never quite satisfying. Why would a ring of star-forming material be tilted 20 degrees out of the galactic plane? What process produced that geometry? And why would it be centered so neatly on our solar system? That last question was the most uncomfortable. A ring of this size, centered on us, implied either a remarkable coincidence or an observational bias, that we were seeing a pattern because of where we stood, not because the pattern was actually there. Proposed explanations piled up over the decades. An ancient supernova impact, a collision with a high-velocity gas cloud, a gravitational disturbance from outside the galactic plane. Each mechanism could be made to work on paper, roughly. None of them fit cleanly. None of them generated the kind of unified agreement that usually accompanies correct models. Some astronomers raised objections quietly. There was always an ad hoc quality to the explanations, a sense that the mechanism was being fitted to the structure rather than predicted from first principles. But the belt itself kept appearing in the data, or appeared to keep appearing, and the alternative was abandoning an organizational framework with no replacement ready. So the Gould Belt persisted, not because it was proven beyond doubt, but because it was useful, familiar, and good enough. Then the measurements got better. This is how most wrong things in astronomy eventually fall apart, not through a single dramatic refutation, but through precision. The Gaia mission, a European Space Agency spacecraft, launched in 2013, began producing distance measurements for stars across the galaxy with accuracy that previous instruments could not approach. At the same time, the BeSSeL Survey was generating precise parallax distances to star-forming regions, using a completely different technique. Together, these campaigns gave astronomers something they had never had before: reliable three-dimensional positions for the molecular clouds that were supposed to make up the Gould Belt. What they found was a problem. When you take the clouds, Taurus, Perseus, Ophiuchus, Orion, and place them in three-dimensional space using actual measured distances rather than assumed ones, they do not form a ring. The ring geometry dissolves. The clouds are not arranged around us in a tilted circle. They are arranged in a different pattern entirely, one that makes no sense within the Gould Belt framework. The belt as a physical structure was not there. This is a specific kind of wrongness worth understanding. The Gould Belt was not fabricated. Nobody invented data. The stars were real. The molecular clouds were real. The associations of young massive stars were real. What was wrong was the shape imposed on them, the interpretive framework that connected them into a ring. When distances were assumed rather than measured, the rings seemed to hold together. When distances were actually measured, it came apart. The structure was a projection artifact, a shape that appeared to exist because of how the observations were made and what assumptions filled the gaps. The unease that had followed the Gould Belt for a century turned out to be correct. The mechanism had never been satisfying because the mechanism did not need to exist. There was no tilted ring. There was no centered structure. There was just a collection of molecular clouds that, when viewed from inside the local bubble with limited distance precision, could be forced into a pattern that was not really there. Remove the forcing, add the precision, and the pattern disappears. What the improved distances revealed instead was something far more coherent and far stranger than a tilted ring. The clouds broke into two distinct families. One of them followed a pattern that stretched in a completely different geometry. Not a circle, not a ring, but something that extended along the Orion Arm in a way that no one had fully recognized before. The second family formed its own separate feature. Neither of them was the Gould Belt. Both of them were real. It took precision distance measurements from spacecraft that did not exist until the 21st century to finally show that the ring was not actually a ring, and what replaced it would reshape the entire picture of how our region of the Orion Arm is organized. In the early 2000s, a group of astronomers began a systematic campaign to settle the question of the Milky Way's spiral structure, using a method that had never been applied at this scale before. The tool they chose was the Very Long Baseline Array. 10 radio telescopes spread across the continental United States, from Hawaii to the Virgin Islands, linked together into a single instrument with a baseline nearly as wide as the Earth itself. No single dish could have done what this network could do. The combined resolution was extraordinary, sharp enough to see, in a rough analogy, a single coin sitting on the surface of the moon. That kind of precision was the whole point. Precision was exactly what the spiral arm problem demanded. The targets were masers, not lasers. Masers, natural radio amplifiers, clouds of gas in regions of active star formation that emit intense beams of microwave radiation at very specific frequencies. They occur where massive stars are being born, where gravity has pulled gas dense enough that certain molecules, water, methanol, lock into configurations that produce these bright, narrow emissions. Because the frequencies are so clean and the signals so intense, masers can be detected across distances that would render ordinary gas clouds invisible. They are, in effect, natural beacons sitting precisely where the survey needed to look, inside the spiral arms, embedded in the star-forming regions that define the arm's structure. The technique the BeSSeL Survey, the Bar and Spiral Structure Legacy Survey, applied to these masers was parallax, the same basic geometry a surveyor uses to measure the distance to a far hilltop by observing it from two separate positions. As the Earth moves around the Sun over the course of a year, nearby objects appear to shift very slightly against the background of distant ones. The amount of that shift depends directly on the distance. Measure the shift, calculate the distance. No assumptions about how the gas is moving, no reliance on velocity models that might be wrong. Pure geometry. The problem was that at distances of thousands of light years, the shift is almost unimaginably small, a fraction of a million cassagant, roughly the apparent size of a baseball observed from across an ocean. The Very Long Baseline Array could measure it anyway. This was the critical difference between what BeSSeL was doing and what had come before. Earlier estimates of the Orion Arm's length had relied on radio observations of hydrogen gas, mapping how that gas was distributed across the sky and inferring distances from how fast it was moving relative to us. That approach required assumptions. You had to assume the gas was following a particular model of how material orbits in a spiral galaxy. If the model was even slightly off, the distances were off. And for something as consequential as the length of a spiral arm, slightly off was not good enough. BeSSeL's parallax measurements required no such assumptions. The distances came directly from geometry that had worked reliably since the Renaissance. When the results began arriving, they were not subtle. The Orion Arm was longer than anyone had measured. Previous estimates based on hydrogen observations had placed the arm at somewhere between 10,000 and 20,000 light-years in length, depending on which model and which dataset you trusted. The BeSSeL Survey results pushed that figure to at least 26,000 light-years. 8 new maser sources were identified within the Orion Arm specifically, extending the arm's mapped extent in both directions from the solar system's position. The arm reached farther toward the galactic core than previous maps showed. It reached farther toward the galactic anticenter. In both directions, the data kept finding structure where earlier observations had seen the arm tapering off. 26,000 light-years. That number carried a specific significance. It is roughly the same as the distance from Earth to the galactic center. The arm that had been described, for decades, as a modest connecting spur between the Perseus and Sagittarius arms, a kind of abbreviated bridge, something the galaxy had sketched in rather than drawn fully, was now, by direct geometric measurement, comparable in length to the spoke of the galaxy it was supposedly sitting between. That was not a spur. That was not a bridge. Whatever it was something that needed to be looked at again. This was not a minor correction to a footnote. When a structure you thought was 10,000 light-years long turns out to be 26,000, you have not refined your measurement. You have fundamentally changed your understanding of the object. The Orion Arm had been quietly filed under minor features of the Milky Way. The BeSSeL numbers pulled it back out of that file. If the arm extended that far, if it hosted that much star-forming material along that continuous length, the old classification required examination. Was it still a spur? Was it a branch of the Perseus arm, as some researchers had begun arguing in 2013? Was it something that deserved its own category entirely? The survey had not settled those questions. In a real sense, it had sharpened them. Every new maser pinned to a precise distance made the arm look more substantial, and a more substantial arm made the labeling problem harder to ignore. The arm that had been quietly labeled a spur for decades was now, by the measurement of geometric distance, longer than the distance from Earth to the center of the galaxy, and the argument about what to call it was no longer purely academic. In January 2020, a paper appeared that required astronomers to throw out a significant portion of what they thought they knew about star formation in our region of the galaxy. It did not come from a new telescope. It did not come from a new wavelength of observation. It came from a team at the Harvard Center for Astrophysics who were doing something deceptively simple, taking known molecular clouds and plotting where they actually sit in three-dimensional space. The Gaia spacecraft had been delivering precise stellar distances for several years by then, and those distances were finally good enough to do something that had never been properly done before. You could take the star-forming clouds in our galactic neighborhood and ask, with real precision, where exactly each one sits. Not roughly, exactly. When the team did that, the answer was not a ring. The Gould Belt model, 150 years old, built into the framework of how astronomers organized their understanding of local star formation, was gone. What replaced it was a wave. The structure, now called the Radcliffe Wave, stretches roughly 9,000 light-years along the Orion Arm. It is a coherent, connected ribbon of gas and dust, and it undulates. That is not a loose description. The structure physically oscillates above and below the galactic plane, rising and falling with an amplitude of roughly 500 light-years on either side of the midplane. If you could see it from outside the galaxy, it would look like a slow ripple moving through the local arm. a frozen wave caught at one moment in what must be a much longer motion. The total gas mass packed into this structure exceeds 3 million times the mass of our Sun. It is the largest coherent structure in our local region of the Milky Way, and until 2020, nobody knew it existed. What makes this genuinely strange is not just the wave's size, it is what is sitting along it. The Taurus molecular cloud is part of the wave. Taurus is only about 400 light-years away, close enough that its individual young stars have been studied in detail for decades. Perseus is part of the wave. The Orion molecular cloud, home to the Orion Nebula, is part of the wave. The massive Cygnus X complex, roughly 5,000 light-years out, is part of the wave. These were treated as separate objects. They had separate entries in catalogues, separate teams studying them, separate literature going back generations. The idea that they were physically connected, strung together along a single oscillating structure like points on a single long curve, was not on anyone's list of possibilities. It should have been visible in the data for years. It was not, because the data lacked the one thing needed to see it: distance, precise distance. Without exact three-dimensional positions, the molecular clouds looked scattered. Spread them out in their true positions, and the wave appears. The Gaia mission provided that precision, and the wave came out of the noise immediately. The Radcliffe Wave is not flat. This matters. A structure 9,000 light-years long that simply traced the galactic midplane would still be remarkable, but it would be easier to explain. The oscillation is the part that demands explanation. The wave does not just run parallel to the plane of the Milky Way's disk. It crosses through the plane, climbs above it, falls back below it, and does this repeatedly along its length with a regularity that implies a physical cause. Something set this structure in motion, and whatever set it in motion did so on a scale that organized 3 million solar masses of gas and dust into a single coherent oscillation spanning thousands of light-years. The solar system is not on the wave. This is worth being specific about. We are sitting slightly to one side, close enough that the nearest reaches of the Radcliffe Wave, the Taurus clouds, are only about 400 light-years away. You could almost say we are watching it from just off the bank. The full wave extends away from us in one direction towards Cygnus, and back in the other through Orion, Perseus and Taurus. Our position inside the local bubble, carved into the inner rim of the Orion Arm, places us slightly offset from this grand structure. We are near enough to study its closest regions in considerable detail. We are not embedded in it. The wave is out there, oscillating, and we are here, observing it from a low-density pocket that keeps us just outside its full extent. The question of what drives the wave's oscillation was not settled in the 2020 paper. That paper established the structure's existence and described its shape. The mechanism remained open. One proposed explanation involves a perturbation from a satellite galaxy passing through or near the Milky Way's disk, generating a large-scale oscillation that propagated through the local interstellar medium. Another possibility is that the wave is a long-lived remnant of some ancient disturbance, a ringing in the disk set in motion hundreds of millions of years ago that has been slowly decaying since. The wave's estimated age runs to around 100 million years, which is consistent with several of these mechanisms. None of them are ruled out. What is clear is that whatever caused it was operating at a galactic scale, not a local one. This was not a cluster of supernovae. This was not a passing molecular cloud. Something large moved through or disturbed the Orion Arm's gas at a scale that reorganized 9,000 light-years of material into a single oscillating structure, and then the wave has been propagating through that material ever since. The Gould Belt model organized 150 years of thinking about nearby star formation around a ring that was not there. The Radcliffe Wave replaced it with something real, something three-dimensional, something that explains the same observations with an actual physical geometry that the data supports. Nobody had seen it before, because nobody had the distance measurements precise enough to see the three-dimensional shape, and the three-dimensional shape turned out to be the whole point. The Radcliffe Wave is not just a new name for an old structure. What the researchers who discovered it concluded was something more fundamental than a relabeling. The wave, they argued, is the primary gas reservoir of the Orion Arm in our local region of the galaxy. That is a different kind of claim. It means the star formation visible in our cosmic neighborhood is not spread randomly through the arm like scattered debris. It is organized. It follows a geometry. The molecular clouds that are right now collapsing into new stars are arranged along a coherent oscillating ribbon, and the shape of that ribbon determines where in the arm new stars will appear and roughly when. Think about what that means for how we read the sky. For generations, astronomers looked at Taurus and Perseus and Orion and Cygnus as separate problems, separate clouds at separate distances, each with its own collapse history, its own internal dynamics, its own reasons for being active. The Radcliffe Wave says that framework was wrong. These regions are not separate. They are connected. They are strung along the same structure the way cities are strung along a river, shaped by the same underlying geography, even when they are hundreds of light years apart. So the first implication is organizational. Star formation in our region of the Orion Arm is not scattered. It has a spine. The second implication is harder. Where did the spine come from? This is where the science becomes genuinely unsettled. The wave is estimated to be roughly 100 million years old, which is young enough in galactic terms that something specific may have set it in motion. One proposed mechanism involves a gravitational perturbation, something massive enough to disturb the interstellar medium across thousands of light years. A satellite galaxy impacting the disk of the Milky Way could do it. The Sagittarius dwarf galaxy has been passing through the Milky Way's disk repeatedly over billions of years, and the timing of at least one of those passages is close enough to the wave's estimated age to be worth examining. The impact of a dwarf galaxy punching through a galactic disk would send oscillations outward through the gas, the way a stone dropped in still water sends rings outward from the point of impact. If that is what happened, the Radcliffe Wave is the ring. It has been moving through the interstellar medium ever since, slowly losing amplitude, still detectable 100 million years later. Another possibility is that the wave is an internal product of the galaxy's own density wave structure. As gas clouds cycle through the spiral arm and get compressed, the dynamics of that compression may naturally produce wave-like arrangements in the resulting star-forming material. The wave in this interpretation is not the result of an external collision, but of the arm's own physics generating an oscillating pattern from the inside. Both mechanisms have problems. Neither has been ruled out. The honest answer is that nobody yet knows what produced the Radcliffe Wave, only that it exists, and that it is old, and that it is real. Then there is the question of what the wave replaced, and this is where the implications become almost disorienting. The Gould Belt, which organized thinking about local star formation for 150 years, was not replaced by the Radcliffe Wave alone. When researchers broke apart the molecular clouds that had been grouped under the Gould Belt model and examined their precise distances, those clouds fell into two distinct structures. One was the Radcliffe Wave. The other was a separate feature, a spur-like structure that researchers have called the split, an apparent secondary feature sitting between the Orion Arm and the inner Sagittarius Carina Arm. Two structures, not one ring. The ring had never been a ring. It was two unrelated features that happened, when viewed with insufficient distance precision, to look like they formed a coherent tilted band around our position. This is not a correction to the Gould Belt model. It is the demolition of it. The observations that fed into it were real. The bright stars were real. The molecular clouds were real. The tilt relative to the galactic plane was real. But the interpretation, the framework that tied all of these observations into a single ring-shaped structure with a physical explanation, was built on geometry that did not actually exist. A century and a half of textbooks, a century and a half of graduate students learning to think about local star formation through this lens, and the structure being described was not there. What is there instead is a wave and a spur, each with its own character and its own dynamics. The Radcliffe Wave is the dominant structure. It carries most of the gas mass. It connects most of the well-known nearby star-forming regions into a single coherent feature. The split is real, but secondary, a separate thread in the same local weave of the arm. And our solar system is outside both of them. The local bubble, that carved-out cavity of thin hot plasma surrounding our position, places us at a slight remove from the densest parts of the wave. The nearest reach of the Radcliffe Wave is the Taurus molecular cloud, roughly 400 light-years out, a dense cold region where stars are forming right now, visible to any telescope pointed in the right direction. Taurus is close enough to study in extraordinary detail, but we are not inside it. We are not inside the wave at all. We are adjacent to it, positioned just outside its main body, looking in from the edge of the local bubble at the nearest terminus of the longest coherent gas structure in our part of the galaxy. The clouds that generations of astronomers studied as separate objects, Taurus, Perseus, Orion, Cygnus, are components of the same oscillating ribbon of gas, and our solar system is sitting just far enough outside it to watch the whole thing from a slight distance. The Orion Arm is not a quiet place. That distinction matters more than it might seem. When astronomers classify the Milky Way's spiral features, they draw a sharp line between what the major arms are and what the Orion Arm is. The Perseus Arm, the Scutum Centaurus Arm, these are dense, massive structures, packed with stellar populations spanning billions of years of age. Old stars, middle-aged stars, young stars, all layered together into thick concentrations of matter that have been building up across most of the galaxy's history. The Orion Arm is something different. It is not a repository of accumulated stellar generations. It is a factory. Its dominant feature is not the stars already burning inside it, but the process of making new ones. Constantly, from the enormous reservoirs of cold gas and molecular cloud material that define its character. This is not a subtle difference. A major arm is like a city that has been growing for centuries, with old neighborhoods pressing against new construction, history embedded in the structure at every level. The Orion Arm is more like a place where the construction itself is the defining activity, where the most important thing happening at any given moment is not what is already built, but what is currently being assembled from raw material. The mechanism driving this is well understood. Molecular clouds, cold, dense concentrations of hydrogen gas and dust, collapse under their own gravity. The collapse accelerates. A core of gas heats up under compression until nuclear fusion ignites, and a star is born. If that star is massive enough, its life plays out fast, tens of millions of years at most, sometimes far less. During that time, it burns at temperatures hot enough to flood the surrounding gas with ultraviolet radiation, stripping electrons from hydrogen atoms and causing the gas to fluoresce. That is what the glowing nebulae scattered across the arm actually are. Vast clouds of ionized gas lit from within by newly formed stars too young to have moved far from where they were born. The radiation does more than illuminate, it pushes. Stellar winds from massive young stars carry enormous momentum outward into the surrounding medium, sweeping gas ahead of them, compressing it into shells and filaments. Those compressed regions become the next generation of molecular clouds. The process is not purely sequential, not a clean chain from one generation to the next. It is tangled, overlapping, with multiple cycles running simultaneously across hundreds of light years, each one feeding back into the others. Star formation in the Orion Arm is not a series of isolated events. It is a continuous, self-propagating process spread across the full length and width of the structure. Massive stars do not go quietly. When a star of 20 or 30 solar masses exhausts its fuel, the collapse happens in under a second. What follows is a supernova, a release of energy that briefly outshines entire galaxies. The shock wave from that explosion travels outward at thousands of kilometers per second, compressing everything it encounters. Gas clouds get squeezed. If the compression is strong enough, they collapse into new stars. The explosion that ends one generation plants the conditions for the next, and the material blasted into space by the supernova is not the same material that went in. It is enriched, loaded with carbon, oxygen, silicon, iron. Dozens of heavier elements forged during the star's life and during the explosion itself. That enriched gas mixes back into the surrounding medium and eventually finds its way into the next cloud, the next collapse, the next star. This is the cycle the solar system came out of. The Sun is not a first-generation star. The oxygen in Earth's atmosphere, the iron in its core, the carbon in every living thing on the planet, none of it was made in the Sun. It was made in previous stars, stars that lived and died before our solar system existed, almost certainly within the same arm structure we still orbit inside today. The molecular cloud that collapsed to form the Sun and planets roughly 4.6 billion years ago was already seeded with the wreckage of earlier generations. We are the downstream product of the Orion Arm's ongoing cycle of destruction and creation. What this means for the environment within the arm is that calm, on the relevant scales, is the exception. Any region of the Orion Arm that looks quiet from a human timescale is quiet only in the way a fast-forward video of a city looks still. The activity is there, but the timescale compresses it into apparent stillness. Across millions of years, the arm is constantly reshaping itself. Clouds collapse and ignite. Massive stars flare and die. Shockwaves propagate. New compressions trigger new collapses. The interstellar medium churns, redistributing gas and dust, and the heavy elements seeded by each generation of dying stars. The Radcliffe Wave, that enormous oscillating ribbon of gas described in the previous section, is itself a feature of this activity, a coherent structure that exists. Because the arm's star-forming processes have a spatial organization, a geometry that links one region of creation to the next across thousands of light years. The local bubble is what happens when this process carves directly into the space around you. At least 15 supernovae, over roughly the last 14 million years, blasted away the interstellar medium in our immediate vicinity. The low-density cavity the solar system now drifts through. The bubble exists because the arm was violent here, recently, on astronomical timescales. The calm we currently occupy is not a natural state of the arm. It is a wound, still healing, its edges marked by compressed gas that is right now forming new stars. Our solar system happens to be in one of the calmer neighborhoods at this particular moment, but that calm was purchased at the cost of at least 15 stellar explosions. The bills from those explosions are still being paid in the form of compressed gas shells that are right now collapsing into new stars at the arm's edges. About 1,340 light-years from Earth, in the sword of Orion, below the three belt stars, something has been visible to the naked eye for as long as humans have had eyes to see it. It looks like a smudge, a slight softening of the sky where a star should be, a faint blur that ancient observers catalogued and moved past without understanding what they were looking at. What they were looking at was a star factory, an active, churning region where new solar systems are being assembled right now, at this moment, while you read these words. The Orion Nebula is not a relic. It is not a remnant of something that happened long ago. It is a process in mid-operation, and it is the closest example of that process to Earth anywhere in the galaxy. The numbers start becoming difficult almost immediately. The nebula spans roughly 25 light-years across. Its mass is approximately 2,000 times the mass of our Sun. It sits 1,340 light-years away, which sounds remote until you compare it to the full length of the Orion Arm, which stretches 26,000 light-years. On that scale, the Orion Nebula is practically in our backyard. This proximity is the reason it has told us more about how stars form than almost any other object in the sky. Distance is the great enemy of resolution in astronomy. The Orion Nebula is close enough that we can see individual young stars, individual disks of gas forming around them, individual structures, smaller than our own solar system, suspended inside a cloud that is still in the act of collapsing. At the center of the nebula, 4 young stars sit together in a tight grouping called the trapezium cluster. These 4 stars are responsible for essentially everything you see when you look at the nebula. They are pouring out ultraviolet radiation at an intensity that ionizes the surrounding gas, stripping electrons from hydrogen atoms and causing the whole cloud to fluoresce. The glow of the Orion Nebula is not reflected starlight. It is the gas itself, excited to luminescence by the 4 stars driving it. Those 4 stars formed within the last few million years. In stellar terms, they are infants. The Sun is about 4.6 billion years old. These stars are, by comparison, brand new. So new that the cloud they formed from has not yet fully dispersed around them. What the trapezium stars are doing to the nebula is something astronomers call photoionization. But the physical picture is straightforward. Intense radiation pushes outward from those 4 central stars in all directions, eating into the surrounding gas cloud, carving a cavity, driving a slow-moving shockwave outward through the molecular material that has not yet been consumed. The edge of that shockwave is where new compression is happening, where gas is being pushed together and forced to collapse. The trapezium stars are, in a very real sense, triggering the formation of the next generation of stars inside the same cloud that made them. About 700 stars in various stages of formation have been identified within the nebula. Many of them are surrounded by protoplanetary disks, the flat rotating envelopes of gas and dust that are the raw material of planetary systems. These disks have been imaged directly. You can see them, dark silhouettes against the glowing background of the nebula, each one a potential solar system in the process of being assembled. The inner regions of those disks are where rocky planets form. The outer regions are where gas giants accumulate. The whole sequence that produced Earth, that produced Jupiter, that produced the asteroid belt, and the comets, and the moons. That sequence is running in hundreds of locations simultaneously inside this cloud, right now. Within 2.5 parsecs of the nebula's center, roughly 1,600 individual sources have been detected and catalogued. The density of young stellar objects in this region is extraordinary. The Orion Nebula is not alone. It is one active face of a much larger structure called the Orion Molecular Cloud Complex, a sprawling region of gas and dust spanning several hundred light-years that contains multiple distinct star-forming zones. The nebula itself sits at the southern end of this complex, the brightest and most active region, but not the only one. There is the Orion B cloud to the east, containing its own embedded clusters and forming stars at its own pace. There are filaments of cold molecular gas threading through the complex that have not yet begun collapsing, but eventually will. The whole system is part of the Radcliffe Wave, the 9,000 light-year oscillating ribbon of gas that was only identified in 2020 and that connects the major star-forming regions of our local galactic neighborhood into a single coherent structure. What the Orion Molecular Cloud Complex illustrates, at a scale you can almost hold in your head, is what the Orion Arm actually is. Not a collection of individual objects, not a scattering of stars and empty space, a continuous, interconnected system of gas clouds, in various states of collapse, with stars forming inside them, those stars driving shock waves into adjacent gas, those shock waves compressing material that then forms new stars. The arm is one long, tangled chain of this process, running for tens of thousands of light-years, with the Orion Nebula as the nearest legible example of what the whole chain is doing. Here is what makes this strange to consider. Our solar system did not form in this nebula, but it formed in something very much like it, a molecular cloud that collapsed under its own gravity, condensed into a disk, ignited a star at its center, and assembled planets from the leftover material. The cloud that made the Sun and the Earth and everything in the solar system was consumed entirely in that process. It does not exist anymore as a cloud. It exists as the Sun, as the planets, as the asteroid belt and the comets and the interplanetary dust. Every molecule of that original cloud is now part of the solar system in some form. The solar system formed in a cloud very much like this one, in a process very much like this one, roughly 4.6 billion years ago. And the original cloud was consumed so completely in making the Sun and planets that not a trace of it remains except for the objects it became. 2 of the 10 brightest stars in the night sky sit within our arm, close enough that on a clear night you can find them with no equipment whatsoever. No telescope, no binoculars, just dark sky, and a few minutes of patience. They are the two brightest points in Orion, one burning red-orange on the hunter's left shoulder, one blazing blue-white at the hunter's right foot. Betelgeuse and Rigel, both supergiants, both residents of the same minor arm our solar system has been traveling through for billions of years. Their presence in our sky is not coincidence. They are here because we share the same galactic address. Betelgeuse sits roughly 700 light-years away. That number sounds enormous, and it is, but inside the Orion Arm it amounts to almost nothing, a short walk across a very large room. The star itself is between 640 and 764 solar radii across, a range that reflects genuine uncertainty in the measurement because the outer atmosphere is so diffuse it has no clean edge. Place it at the center of the solar system, and the surface of Betelgeuse extends past Mercury, past Venus, past Earth, past Mars. The asteroid belt disappears inside it. You would need to travel out to roughly the orbit of Jupiter before you found yourself outside the star. Everything we consider home sits well within its interior. The Sun, by comparison, would be a marble lost somewhere in that glowing plasma ocean. Rigel is farther out, closer to 860 light-years, but distance is doing almost nothing to dim it. Rigel is one of the most luminous stars in the Milky Way, putting out roughly 120,000 times the energy of our Sun. If you moved Rigel to the distance of Sirius, about 8.6 light-years, it would outshine Venus in the night sky by a significant margin. It is a blue-white supergiant, hotter and more massive than Betelgeuse, burning through its hydrogen with an intensity that makes our Sun look conservatively managed. When you see that cold blue-white point at the foot of Orion, you are looking at a star spending its fuel at a rate that cannot last. The contrast between them is the thing worth holding onto. Betelgeuse is red, Rigel is blue-white. These are not arbitrary colors, they are temperature indicators, and temperature tells you where a star is in its life. Rigel is blazing hot, still on the main sequence in the broad sense, a massive star in the full force of its existence. Betelgeuse has already exhausted its core hydrogen and swollen outward into that enormous red envelope, a star at the end of a long sequence of internal changes that only ends one way. Both are supergiants, but they represent completely different moments in the same trajectory. One is arriving, one is nearly done. Neither of them will be here long. This is the key fact. Stars this massive burn fast. Where our Sun has been fusing hydrogen quietly for 4.6 billion years, and has billions more years remaining, stars like Rigel and Betelgeuse measure their total lifespans in millions of years. Betelgeuse is already somewhere between 8 and 10 million years old, which for a star of its mass is ancient. Rigel is younger, still in an earlier stage of its evolution, but even Rigel is operating on a timescale that makes the Sun look immortal by comparison. Both will end in supernova. The question is only when. The presence of stars like these throughout the Orion Arm tells you something specific about the arm itself. Massive, short-lived stars do not travel far from where they were born. They ignite, burn brilliantly, and explode, all within a few million years, before they have time to migrate far from their formation sites. The fact that Betelgeuse and Rigel are sitting relatively close to us means star formation in this region of the arm has been active recently enough, in stellar terms, to produce this current generation of massive objects. They are evidence of the arm's ongoing activity, markers of a region that has been building new stars continuously enough to keep populating the local volume with massive luminous objects. The belt stars of Orion, Alnitak, Alnilam, Mintaka, are part of the same picture. All three are hot blue supergiants. Alnitak alone is roughly 800 light-years away and about 100,000 times as luminous as the Sun. These are not background objects scattered randomly through the arm. They are members of the Orion OB1 Association, a loose grouping of massive stars that form together from the same molecular cloud complex, the same reservoir of gas and dust that produced the Orion Nebula. The arm's character, its identity as a star-forming structure, is written directly in the brightness of the stars above us on a winter night. Betelgeuse is the strangest case. At 700 light-years, It is the closest red supergiant to Earth, and it has become the most studied star of its type in the universe. Observations from every major telescope on Earth and in space have been directed at it. The dimming event of 2019 and 2020 drew global attention. It has revealed details about how red supergiants behave internally, the massive convection cells churning in its outer layers, the dust-shedding events, the oscillations that no other star of its type has yielded at this level of detail. Its proximity within the arm is why any of that study was possible. It is a dying giant sitting practically next door to us in galactic terms, offering a front-row view of a process that ends in one of the most violent events the universe produces. Both of them will be gone from the sky within a few million years. A brief flash of massive stellar life playing out inside the same minor arm that our own much quieter sun has been orbiting through for 4.6 billion years. There is a question hiding underneath all of this that most descriptions of the Orion Arm never quite answer. Why does it stay together at all? The galaxy does not rotate like a solid disk. A planet closer to the Sun orbits faster than a planet farther away, and the same principle applies across the entire Milky Way. Stars near the galactic center complete their orbits in far less time than stars sitting out in the disk where the Orion Arm runs. If the spiral arms were fixed structures, specific stars locked together, rotating as a rigid unit, this differential rotation would tear them apart. The inner stars would race ahead, the outer stars would fall behind, and within a few rotations the arm would wind itself into oblivion. On a galactic timescale, a few rotations is not long, and yet the arms are still there. They do not wind up, they do not dissolve. Something is keeping them coherent, and that something is not what most people assume. The answer came from two mathematicians working at MIT in the 1960s. C.C. Lin and Frank Shu proposed that spiral arms are not collections of specific stars moving together. They are waves, density waves, regions of slightly elevated gravitational pressure that rotate through the galactic disk at their own speed, independent of the individual stars and gas clouds that pass through them. The stars are not the arm. The arm is a condition that stars and gas pass through, briefly, before moving on. The clearest analogy is a traffic jam on a long highway. Far ahead of the jam, traffic moves freely. Far behind it, traffic moves freely. But in one region of the road, cars have slowed. They bunch together, the density is higher. Now here is the key. The cars are not stuck. Each car moves through the jam, slows while inside it, and then accelerates again on the other side. Individual cars are constantly entering from the rear and exiting from the front. The jam itself, though, persists. It holds its position on the highway, or drifts slowly, even as every specific car that makes it up changes from minute to minute. The jam is a feature of the road, not a property of any particular vehicle. Spiral arms work the same way. The density wave rotates through the galactic disk at a specific pattern speed. Gas clouds orbiting the galaxy at their own speeds eventually catch up to the wave, or the wave overtakes them, depending on their distance from the center. As a cloud enters the higher density region, it gets compressed. That compression matters enormously. Molecular gas that had been drifting through space in a stable, diffuse state suddenly finds itself squeezed. Pressure builds. Temperatures shift. In the densest pockets, gravity wins, and the cloud begins to collapse. Stars ignite. The most massive of them blaze with extraordinary ultraviolet output, ionizing the surrounding gas and making it glow. From a distance of thousands of light years, those glowing regions mark the arm's location. But the stars that light up the arm will not stay inside it. They form inside the density wave, burn brilliantly for a few million years, and then drift out the other side. New gas clouds are always entering. New stars are always being born. The arm glows continuously, not because it holds the same material, but because it keeps making new material luminous. This is what the Orion Arm actually is, not a fixed structure of permanent residence, a region where compression happens, where star formation concentrates, where gas clouds are pushed past a threshold and forced into collapse. Betelgeuse, Rigel, the Orion Nebula, the Radcliffe Wave, these are all artifacts of that compression, objects and structures that exist because gas moving through this region of the galaxy encountered elevated density and responded to it. Our solar system is inside this wave right now, but the Sun has not always been inside it, and it will not stay inside it. The Sun orbits the galactic center at roughly its own pace, and the density wave pattern rotates at a different pace. Over billions of years, these two rates interact. The Sun drifts into the arm, spends time within it, and eventually drifts out into the quieter inter-arm regions before the geometry of the orbit brings it back around into another arm entirely. Over 4.6 billion years, the Sun has passed through multiple spiral arms. The Orion Arm is simply the one it happens to be crossing right now. What that means is worth holding still for a moment. The arm is not a home, it is a crossing. The Sun entered the Orion Arm's density wave region at some point in the relatively recent past on galactic timescales, and it will exit at some point in the future. The stars we see anchoring the arm around us, the supergiants, the bright clusters, the glowing nebulae, are the current generation of objects that the arm has produced. Previous generations formed and died before our solar system arrived. Future generations will form after we have moved on. The last time the Sun was roughly where it is now in its galactic orbit was about 230 million years ago, when the most complex life forms on Earth were the ancestors of the first dinosaurs. And the Orion Arm the Sun passed through then was full of entirely different stars, different clouds, different stellar nurseries that have long since lived and died. The solar system is not sitting still inside the Orion Arm. It is moving through it at roughly 515,000 miles per hour, a speed that has no meaningful comparison in ordinary human experience. A commercial jet flies at about 575 miles per hour. The fastest spacecraft ever launched, Voyager 1, travels at around 38,000 miles per hour. The solar system is moving 13 times faster than that, continuously in a vast curve around the galactic center. And even at 515,000 miles per hour, one complete orbit takes approximately 230 million years. That number needs to sit for a moment. Astronomers sometimes call this a galactic year, or a cosmic year. One galactic year is 230 million years of continuous motion, at a speed no human technology has come close to achieving. The solar system has existed for roughly 4.6 billion years. In that time, it has completed approximately 20 of these orbits, 20 laps around the center of the Milky Way, each one taking longer than the entirety of the Cambrian explosion. The age of fish, the age of amphibians, the age of reptiles, the age of dinosaurs, the age of mammals, everything that has ever lived on this planet combined, with time left over. One galactic year ago, Earth was a very different place. The Permian extinction had just ended, the single most catastrophic mass extinction in the planet's history. Somewhere between 90 and 96% of all marine species had been wiped out. Life was rebuilding from almost nothing. The Triassic period was just beginning. The earliest ancestors of the dinosaurs were beginning to take shape in a world still recovering from collapse. That was one galactic year ago. The solar system was in roughly the same position in its orbit that it occupies today, moving through the same region of the galaxy. Since then, every dinosaur that ever lived has appeared, dominated the planet, and vanished. Every mammal lineage has evolved and diversified. The entire human story, from the first stone tools to the radio telescopes now mapping the arm we live in, has laid out inside a single galactic year. That is the timescale of one orbit. The motion is not simple. The solar system does not trace a clean, flat circle around the galactic center. It weaves. As it orbits, it bobs above and below the galactic plane, oscillating like a slow wave with a period of roughly 70 million years. Right now, the Sun sits slightly north of the galactic midplane, maybe 50 to 100 light-years above the average plane of the disk. That sounds like a large distance. On the scale of the galaxy, it is almost nothing. This bobbing motion has consequences. The galactic disk is not uniformly dense throughout its thickness. The midplane region contains the highest concentration of gas, dust, and molecular clouds. Moving above and below it means the solar system periodically passes through regions of different density. When the Sun dips closer to the midplane, it moves through more crowded interstellar territory. When it rises above, the surroundings thin out. Some researchers have proposed that this oscillation is not cosmetically neutral, that periodic passages through denser regions of the disk could disturb the outer solar system, nudging distant comets inward. The idea has been explored in connection with periodic extinction events in Earth's fossil record, though the evidence remains contested and the connections are still debated among specialists. What is not debated is the basic geometry. The solar system is moving, bobbing, weaving, covering enormous distances every year, every century, every million years. And because the density wave that defines the Orion Arm is itself rotating, the solar system is orbiting at its own speed. The relationship between the two is not fixed. The Sun does not orbit at the same rate that the Arm's density wave rotates. The two speeds are different. That means the solar system gradually drifts through the Arm, rather than being permanently anchored inside it. Think of it like two gears rotating at slightly different speeds. The Sun moves through the Arm, eventually crossing its inner edge, spending time in the interarm region, then eventually entering the next arm inward or outward. The crossing of a spiral arm is not a sudden event. It takes tens of millions of years to move through the full width of one. The solar system entered the Orion Arm at some point in the distant past. It will exit the arm at some point in the distant future. That transition will be utterly imperceptible to anything living through it, because the arm is so wide and the motion is so gradual. In its 4.6 billion years, the Sun has passed through the Milky Way's major arms multiple times. Each passage brought different stellar neighborhoods, different densities of gas and dust, different radiation environments. The Orion Arm is simply the arm the solar system happens to be crossing right now. It is not where the solar system was born, necessarily. It is not where the solar system will end. It is a structure we moved into, are moving through. Will one day move out of entirely, on a timescale so long that the species doing the measuring may not exist on either end of it. The Arm is not our permanent home in any meaningful sense. It is a region we are passing through, have been passing through for millions of years, will one day leave behind entirely. Moving into the emptier space between the Orion Arm and the Perseus Arm before the galactic orbit eventually brings us back. The Orion Arm does not exist in isolation. It sits wedged between two structures that dwarf it completely, pressed into the space between a major interior arm and a major exterior arm, like a thin seam between two thick planks. To understand what the Orion Arm actually is, why the solar system feels so isolated within it, you need to understand what is on either side of it. Toward the galactic interior, in the direction of Sagittarius, toward the center of the Milky Way, lies the Carina-Sagittarius Arm. It runs roughly 5,000 to 7,000 light-years inward from our position, curving around the galactic core in a sweeping arc visible in radio wavelengths. As one of the brighter features of the inner galaxy, it is denser than the Orion Arm, more populated. The star-forming regions it contains are correspondingly more active, the concentrations of molecular gas more tightly packed. In the other direction, outward, away from the galactic center, toward the constellation Perseus, lies the Perseus Arm. This is one of the two primary spiral arms of the Milky Way. It sits roughly 6,000 to 7,000 light-years away from us. On radio maps of the galaxy, it resolves as a thick, continuous arc of emission, populated by enormous stellar associations and massive star-forming complexes that make our local regions look sparse. The Orion Arm lies between them, not centered between them, not dramatically positioned, just occupying the available space, thinner and less defined, a minor feature running through the gap. What that means for us practically is something worth thinking through carefully. We are not in either of the dense structures surrounding us. We are in the thinner region between them, close to the inner edge of our own minor arm, sitting inside the local bubble. That is itself a carved-out cavity of below-average density. Density in this context means interstellar gas, molecular clouds, concentrations of young stars. The Sagittarius arm has more of all of these per unit volume. The Perseus arm has more. The Orion arm has less, and the specific pocket of the Orion arm that our solar system occupies has less still. Now consider what this looks like from somewhere else. Imagine standing on a planet at the inner edge of the Perseus arm, 6,000 light-years outward from here. Looking back toward the galactic center, you would see the Orion Arm. It would appear as a faint, diffuse band of light and radio emission, thinner than the arm you were standing in, less densely populated, harder to distinguish cleanly from the interarm medium surrounding it. Our Sun would be one unremarkable point among a sparse distribution of stars in that faint feature. Nothing about its position would draw attention. From the galactic center itself, 26,000 light-years away, the geometry gets more extreme. The major arms would dominate the view of the disk, their dense stellar populations and glowing star-forming complexes forming the most visible structural features of the galaxy. The Orion Arm, from that distance and in that context, would be a faint thread. Whether it would even register clearly as a separate structural feature against the background disk emission is genuinely uncertain. The major arms have enough mass and brightness to stand out from the disk at large distances. The Orion Arm may not. The most striking version of this problem is what you see when you photograph other galaxies. Images of M81, the Andromeda Galaxy, M51, and similar spirals show clean, dramatic arm structures. 2 or 4 primary arms wrapping around a bright central region, glowing with young blue-white stars and pink emission nebulae. These images have shaped the popular picture of what a spiral galaxy looks like. What they are actually showing is the major arms, the minor arms, the spurs, the connecting features between the dominant structures. They are there, but they do not dominate the image. They are lost in the background. If you were photographing the Milky Way from a distance of a few million light-years, with the same techniques used to image those other galaxies, the Perseus arm would be visible, the Carina Sagittarius arm would be visible, the Orion arm would be a faint, easily overlooked smear of emission between them, if it appeared clearly at all. Our solar system, sitting in that smear, would not be locatable. It would be in the interarm region from the perspective of how the image reads. This is not a small point. It means that everything that makes our night sky feel populated, the band of the Milky Way stretching overhead, the dense star fields, the glowing patches of nebulosity, much of that light comes from the direction of the galactic center and the major arms surrounding us. We are looking outward and inward at structures more massive than our own. The Sagittarius arm contributes to the bright band of the Milky Way that runs through Sagittarius and Scorpius. The Perseus arm contributes in the other direction. The Orion arm itself provides our most immediate stellar neighbors, the stars visible to the naked eye at moderate distances. But the overwhelming weight of the galaxy's light comes from the major structures on either side. Our immediate sky is shaped by where we sit, between 2 major arms, slightly inward within our own minor one, inside a bubble of cleared-out gas that leaves our local region quieter than most of the arm around us. The glow we call the Milky Way is largely someone else's neighborhood. When astronomers photograph other spiral galaxies and see the major arms lit up with brilliant blue-white star clusters and glowing pink nebulae, they are seeing the equivalent of the Perseus and Sagittarius arms. The Orion arm equivalent in those galaxies would be the faint, easily overlooked feature between them. Step back far enough from the Orion arm, and it nearly disappears. The Milky Way is estimated to be somewhere between 100,000 and 200,000 light-years across. Its central bar alone, the thick, elongated structure of stars running through the galaxy's core, stretches roughly 27,000 light-years from end to end. The major spiral arms, the ones that define the galaxy's shape from outside, wrap around the galactic center for approximately 80,000 light-years each. Against those numbers, the Orion Arm, even at its newly revised length of 26,000 light-years, is a secondary feature, a detail, something you might notice if you were looking carefully, and overlook entirely if you were not. If you treated the Orion Arm as a rough rectangle and calculated what fraction of the Milky Way's disk area it occupies, the answer comes out to around 1.5%. The Milky Way contains somewhere between 100 billion and 400 billion stars. The Orion Arm holds a fraction of those, an uncertain fraction, but clearly a small one. The arm is not where most of the galaxy's mass is. It is not where most of the galaxy's stars are. It is a thinner, younger, gas-rich structure filling the space between two major arms, more active in star formation than in accumulated stellar population, more notable for what it is producing than for what it has already built up. Most people's mental picture of a spiral galaxy comes from photographs. M51, the Whirlpool Galaxy. NGC 1300, with its long sweeping bar. Andromeda, stretched across a dark sky in long exposure images. These photographs show clean, dramatic spiral arms, bright with clusters and nebulae, winding outward in elegant curves from a glowing core. That image is not wrong, but it creates a specific expectation that a spiral galaxy consists of a center and a set of prominent arms, that the structure is fairly simple. The Milky Way does not cooperate with that expectation. Astronomers now classify the Milky Way as a barred spiral galaxy. Instead of arms emerging directly from a central bulge, the Milky Way has a thick bar of stars running through its core. The primary arms attach to the ends of that bar. The Scutum Centaurus arm connects to one end. The Perseus arm connects to the other. Two additional arms, Norma and Sagittarius, fill in parts of the structure as secondary features. The Orion Arm sits between Sagittarius and Perseus, a thinner spur woven into the interarm region. In photographs of comparable galaxies, structures like the Orion Arm register as faint wisps between the brighter dominant features. Easy to miss, easily categorized as secondary. The galaxy also does not exist alone. The Milky Way has satellite galaxies, smaller systems orbiting it, pulled close by gravity, interacting with the primary structure in ways that are still being untangled. The Large and Small Magellanic Clouds are the most visible of these. Two irregular dwarf galaxies orbiting the Milky Way at distances of roughly 160,000 and 200,000 light-years. They are close enough to see with the naked eye from the southern hemisphere, smeared across the sky like detached fragments of the Milky Way itself. Their gravitational influence on the Milky Way's disk is measurable. Their eventual fate is collision and absorption. Then there is the Sagittarius dwarf galaxy. Unlike the Magellanic Clouds, the Sagittarius dwarf is not a clean satellite at a safe distance. It is in the process of merging with the Milky Way right now. Its stars are being stretched into long streams, pulled apart by tidal forces, woven into the Milky Way's outer disk in ribbons that wrap around the galaxy multiple times. Some researchers have proposed that the Sagittarius dwarf's repeated close passes through the Milky Way's disk may have triggered or reinforced the spiral arm structure we see today, that the arms themselves are partly a response to this ongoing collision. If that is correct, the Orion Arm may owe some part of its existence to a merger that has been playing out across hundreds of millions of years. None of this is static. The galaxy is not a fixed object. It is a system in motion, evolving over billions of years, absorbing smaller galaxies, reshaping its own arms, changing its star-forming patterns as the distribution of gas shifts across deep time. In roughly 4 billion years, the Milky Way and the Andromeda Galaxy will begin to merge, a collision of two large spiral galaxies that will eventually produce a single elliptical system. The spiral arms, the bar, the minor features like the Orion Arm, all of it will be disrupted and ultimately unrecognizable. The Milky Way itself is not an isolated system. It belongs to the local group, a collection of more than 50 galaxies bound together by gravity, dominated by the Milky Way and Andromeda. The local group sits within the Virgo supercluster, a broader concentration of galaxy groups spanning roughly 110 million light-years. And the Virgo supercluster is itself a minor component of the Laniakea supercluster, a vast web of galaxies spanning 520 million light-years, containing the mass of roughly 100 million billion suns. The solar system is in the Orion Arm. The Orion Arm is in the Milky Way. The Milky Way is in the local group. The local group is in the Virgo supercluster. The Virgo supercluster is in Laniakea. Every level of zoom reveals a structure that contains the previous one. At each level, the solar system ends up in a quieter, less central, more obscure position, a pattern that keeps repeating until you run out of larger structures to contain it. There is something worth sitting with at the end of all these numbers. The solar system is not lost in the way that word usually implies, adrift, without structure, without context. The structure is there. The Orion Arm is real, measurable, mapped across 26,000 light-years of gas and dust and stellar nurseries. The problem is not the absence of structure. The problem is that the structure is so large that being inside it produces the same practical effect as being nowhere at all. The local bubble sits around us like a carved-out room. Its walls are hundreds of light-years away. Inside those walls, the gas density drops to roughly 1/10 of what fills the rest of the arm. Our nearest stellar neighbors, Alpha Centauri at 4 light-years, Sirius at 8, Vega at 25, are scattered through this thinned-out region like widely spaced objects in a warehouse too large to see across. These are the close ones. The arm itself extends tens of thousands of light-years beyond them in directions we cannot observe directly. The far end of the Orion Arm is so remote that light leaving it right now will not reach us for 26,000 years. We have no way to see what is happening there. We have no way to know. The Radcliffe Wave runs roughly 9,000 light-years along the arm, the nearest great chain of star formation in our galactic neighborhood. Its closest point, the Taurus molecular cloud, sits about 400 light-years away. That is close enough to resolve individual protostars with modern telescopes. It is also close enough that the wave appears to us not as a wave at all, but as scattered patches of brightness across certain parts of the sky. The three-dimensional shape only became visible when precision distance measurements were finally good enough to place each cloud in its correct position. Before that, the wave was invisible inside the very data describing it. This is the specific quality of the lostness. It is not emptiness in the sense of nothing being present. The Orion Arm is full of molecular clouds, supernova remnants, young stellar clusters, the glowing shells of carved-out bubbles, the dense knots of collapsing gas that will become stars in a few million years. The arm is producing new solar systems right now. It has been producing them continuously for its entire existence. The lostness is something different. It is the lostness of being embedded so deeply inside a structure that the structure's own shape becomes inaccessible. You can measure pieces of it. You can map the nearest few thousand light-years with extraordinary precision. But the full geometry, the true outline, that remains inferred, modeled, argued over. The map keeps changing because the vantage point never does. Every number in this story came from here. The 3,500 light-year width, the 26,000 light-year length, the 1/10 density of the local bubble, the 9,000 light-year extent of the Radcliffe Wave, the distance to the galactic center, the revised position of the arm's inner rim. All of it was calculated from a single location. One planet, orbiting one star, sitting in a carved-out hollow on the inner edge of a minor spiral feature. Astronomers did not step outside to take the measurement. They could not. Every instrument ever aimed at the Orion Arm was built on the surface of a world that is itself part of the Orion Arm. Every observation was made from inside the object, under observation. That is a strange kind of knowing. It is not the knowing of someone looking at a map. It is the knowing of someone who drew the map without ever leaving the territory. using only what could be seen from one fixed corner of it. And yet the measurements kept coming, the tools improved, the parallax precision of the BeSSeL survey, the three-dimensional cloud positions from Gaia, the maser distances that extended the arm's known length by a factor of 4, all of it extracted from this one vantage point, revised again and again, each revision closer to a truth that can never be directly confirmed. All of it, every dimension, every discovery, every revision to the maps, was worked out from a single pale dot sitting in a bubble of carved-out emptiness on the inner edge of a minor arm. And somehow that has been enough to begin to see the shape of the thing we are inside.